Welcome back. In the last few videos, we've been working through creating a model for a classification problem. And now we're up to training a model. And we've got some steps here, but we started off by discussing the concept of logits. Logits are the raw output of the model, whatever comes out of the forward functions of the layers in our model. And then we discussed how we can turn those logits into prediction probabilities using an activation function, such as sigmoid for binary classification and softmax for multi-class classification. We haven't seen softmax yet, but we're going to stick with sigmoid for now because we have binary classification data. And then we can convert that from prediction probabilities to prediction labels. Because remember, when we want to evaluate our model, we want to compare apples to apples. We want our model's predictions to be in the same format as our test labels. And so I took a little break after the previous video. So my Colab notebook has once again disconnected. So I'm just going to run all of the cells before here. It's going to reconnect up here. We should still have a GPU present. That's a good thing about Google Colab, is that if you change the runtime type to GPU, it'll save that wherever it saves the Google Colab notebook, so that when you restart it, it should still have a GPU present. And how can we check that, of course? Well, we can type in device, we can run that cell, and we can also check NVIDIA SMI. It'll tell us if we have an NVIDIA GPU with CUDA enabled ready to go. So what's our device? CUDA, wonderful. And NVIDIA SMI, excellent. I have a Tesla P100 GPU ready to go. So with that being said, let's start to write a training loop. Now we've done this before and we've got the steps up here. Do the forward pass, calculate the loss. We've spent enough on this, so we're just going to start jumping into write code. There is a little tidbit in this one though, but we'll conquer that when we get to it. So I'm going to set a manual seed, torch.manual seed, and I'm going to use my favorite number 42. This is just to ensure reproducibility if possible. Now I also want you to be aware of, there is also another form of random seed, manual seed, which is a CUDA random seed. Do we have the PyTorch? Yeah, reproducibility. So torch.cuda.manualseed.seed. There is a CUDA seed somewhere. Let's try and find out. CUDA. I think PyTorch have just had an upgrade to their documentation. Seed. Yeah, there we go. Okay. I knew it was there. So torch.cuda.manual seed. So if we're using CUDA, we have a CUDA manual seed as well. So let's see what happens if we put that, torch.cuda.manual seed 42. We don't necessarily have to put these. It's just to try and get as reproducible as numbers as possible on your screen and my screen. Again, what is more important is not necessarily the numbers exactly being the same lining up between our screens. It's more so the direction of which way they're going. So let's set the number of epochs. We're going to train for 100 epochs. Epochs equals 100. But again, as you might have guessed, the CUDA manual seed is for if you're doing operations on a CUDA device, which in our case we are, well, then perhaps we'd want them to be as reproducible as possible. So speaking of CUDA devices, let's put the data to the target device because we're working with, or we're writing data agnostic code here. So I'm going to write xtrain ytrain equals xtrain to device, comma, ytrain dot to device. That'll take care of the training data. And I'm going to do the same for the testing data equals xtest to device. Because if we're going to run our model on the CUDA device, we want our data to be there too. And the way we're writing our code is going to be device agnostic. Have I said that enough yet? So let's also build our training and evaluation loop. Because we've covered the steps in here before, we're going to start working a little bit faster through here. And don't worry, I think you're up to it. So for an epoch in a range of epochs, what do? We start with training. So let me just write this. Training. Model 0.train, that's the model we're working with. We call the train, which is the default, but we're going to do that anyway. And as you might have guessed, the code that we're writing here is, you can functionize this. So we're going to do this later on, but just for now, the next couple of videos, the next module or two, we're going to keep writing out the training loop in full. So this is the part, the forward pass, where there's a little bit of a tidbit here compared to what we've done previously. And that is because we're outputting raw logits here if we just pass our data straight to the model. So model 0 x train, and we're going to squeeze them here to get rid of an extra dimension. You can try to see what the output sizes look like without squeeze, but I'm just going to call squeeze here. Remember, squeeze removes an extra one dimension from a tensor. And then to convert it into prediction labels, we go torch.round and torch.sigmoid, because torch.sigmoid is an activation function which is going to convert logits into what? Convert the logits into prediction probabilities. So y logits, and I'm just going to put a note here. So this is going to go turn logits into pred probs into pred labels. So we've done the forward pass. So that's a little tidbit there. We could have done all of this in one step, but I'll show you why we broke this apart. So now we're going to calculate loss/accuracy. We don't necessarily have to calculate the accuracy, but we did make an accuracy function up here so that we can calculate the accuracy during training. We could just stick with only calculating the loss, but sometimes it's cool to visualize different metrics, loss plus a few others while your model is training. So let's write some code to do that here. So we'll start off by going loss equals loss fn and y logits. Here's the difference of what we've done before. Previously in the notebook 01, we're up to 02 now, we passed in the prediction right here. But because what's our loss function? Let's have a look at our loss function. Let's just call that, see what it returns. BCE with logits loss. So the BCE with logits expects logits as input. So as you might have guessed, loss function without logits, if we had nn.bce loss, notice how we haven't got with logits, and then we called loss fn, fn stands for function by the way, without logits, what do we get? So BCE loss. So this loss expects prediction probabilities as input. So let's write some code to differentiate between these two. As I said, we're going to be sticking with this one. Why is that? Because if we look up torch BCE with logits loss, the documentation states that it's more numerically stable. So this loss combines a sigmoid layer and the BCE loss into one single class and is more numerically stable. So let's come back here. We'll keep writing some code. And the accuracy is going to be accuracy fn. So our accuracy function, there's a little bit of a difference here, is y true equals y trained for the training data. So this will be the training accuracy. And then we have y pred equals y pred. So this is our own custom accuracy function that we wrote ourselves. This is a testament to the Pythonic nature of PyTorch as well. We've just got a pure Python function that we've slotted into our training loop, which is essentially what the loss function is behind the scenes. Now, let's write here, nn.bce with logits loss expects raw logits, so the raw output of our model, as input. Now, what if we were using a BCE loss on its own here? Well, let's just write some code for that. So let's call loss function, and then we want to pass in y pred, or we can just go y or torch sigmoid. So why would we pass in torch sigmoid on the logits here? Because remember, calling torch.sigmoid on our logits turns our logits into prediction probabilities. And then we would pass in y train here. So if this was BCE loss, this expects prediction probabilities as input. So does that make sense? That's the difference between with logits. So our loss function requires logits as input, whereas if we just did straight up BCE loss, we need to call torch.sigmoid on the logits because it expects prediction probabilities as input. Now, I'm going to comment that out because our loss function is BCE with logits loss. But just keep that in mind. If for some reason you stumble across some PyTorch code that's using BCE loss, not BCE with logits loss, and you find that torch.sigmoid is calling here, or you come across some errors because your inputs to your loss function are not what it expects. So with that being said, we can keep going with our other steps. So we're up to optimizer 0 grad. So optimizer.0 grad. Oh, this is step 3, by the way. And what's after this? Once we've 0 grad the optimizer, we do number 4, which is loss backward. We can go loss backward. And then we go, what's next? Optimizer step, step, step. So optimizer.step, and I'm singing the unofficial PyTorch optimization loop song there. This is back propagation. Calculate the gradients with respect to all of the parameters in the model. And the optimizer step is update the parameters to reduce the gradients. So gradient descent, hence the descent. Now, if we want to do testing, well, we know what to do here now. We go model 0, what do? We call model.eval when we're testing. And if we're making predictions, that's what we do when we test. We make predictions on the test data set using the patterns that our model has learned on the training data set. We turn on inference mode because we're doing inference. We want to do the forward pass. And of course, we're going to compute the test logits because logits are the raw output of our model with no modifications. xtest.squeeze. We're going to get rid of an extra 1 dimension there. Then we create the test pred, which is, we have to do a similar calculation to what we've done here for the test pred, which is torch.round. For our binary classification, we want prediction probabilities, which we're going to create by calling the sigmoid function on the test logits. Prediction probabilities that are 0.5 or above to go to 1, and prediction probabilities under 0.5 to go to label 0. So 2 is calculate the test loss /accuracy. How would we do this? Well, just as we've done before. And we're going to go loss fn test logits, because our loss function we're using what? We're using BCE with logits loss, expects logits as input. Where do we find that out? In the documentation, of course. And then we come back here. Test logits, we're going to compare that to the y test labels. And then for the test accuracy, what are we going to do? We're going to call accuracy fn on y true equals y test and y pred equals test pred. Now you might be thinking, why did I switch up the order here for these? Oh, and by the way, this is important to know with logits loss. So with these loss functions, the order here matters of which way you put in your parameters. So predictions come first and then true labels for our loss function. You might be wondering why I've done it the reverse for our accuracy function, y true and y pred. That's just because I like to be confusing. Well, not really. It's because if we go to scikit-learn, I base a lot of my structured code off how scikit-learn structures things. The scikit-learn metrics accuracy score goes y true, y pred. So I based it off that order because the scikit-learn metrics package is very helpful. So I've based our metric, evaluation metric function, off this one. Whereas PyTorch's loss function does it in the reverse order, and it's important to get these in the right order. Exactly why they do it in that order, I couldn't tell you why. And we've got one final step, which is to print out what's happening. Happening. So how about we go, we're doing a lot of epochs here, 100 epochs. So we'll divide the epoch by 10 to print out every epoch, or every 10th epoch, sorry. And we have a couple of different metrics that we can print out this time. So we're going to print out the epoch number, epoch, and then we're going to print out the loss. So loss, how many decimal points? We'll go 0.5 here. This is going to be the training loss. We'll also do the accuracy, which will be the training accuracy. We could write train acc here for our variable to be a little bit, make them a little bit more understandable. And then we go here, but we're just going to leave it as loss and accuracy for now because we've got test loss over here. Test loss. And we're going to do the same, 5 decimal points here. And then we're going to go test accuracy as well. Test acc dot. We'll go 2 for the accuracy. And because it's accuracy, we want a percentage. So this is the percent out of 100 guesses. What's the percentage that our model gets right on the training data and the testing data, as long as we've coded all the functions correctly. Now, we've got a fair few steps here. My challenge to you is to run this, and if there are any errors, try to fix them. No doubt there's probably 1 or 2 or maybe more that we're going to have to fix in the next video. But speaking of next videos, I'll see you there. Let's train our first classification model. Oh, this is very exciting. I'll see you soon.